dice has 6 faces, right? So we can represent the points on each side of the dice. It's 1, 2, 3, 4 until 6, right? So outcomes for this rolling dice experiment has 6 elements. And also if you toss a coin, then the space, the sample space will be consisting only 2 elements, head or tail. And if you are interested in the temperature in Salt Lake City, then what are the sample space? It is all possible. It's just real numbers, right? Because temperature are real numbers. It is continuous sample space. Consists of infinite, uncountable numbers. And why would we use a mapping to represent the random variables? Because we want to build up a mathematical framework to characterize the uncertainty of the random variables and also derive or infer the relationship between multiple random variables. Right? We can only do this in mathematical domains. Math cannot directly operate on your dice, cannot directly operate on your coin, right? So before we build up a mathematical theory for that, we must first map these observations into some mathematical numbers. Then we can build up theory on numbers. That's why from mathematical language, we should define the random variables like this. But usually when we talk about random variables, we usually just talk about what kind of values random variables can take, meaning that what kind of values in S can be mapped. Right? So this is about definition of random variable and sample space. And then based on sample space, we can define events, random events. For example, if our interesting experiments is rolling a dice, right? I can come out random events to be like the points in the face is odd, right? Odd dice point. And if we are interested in marrying looking into the temperature in Salt Lake City, right? And one event could be the temperature is between, let me just use T to represent temperature, is between like 72 to 78, right? So this is another type of event. And then, how can we represent events in terms of mathematical operations or mathematical concepts? How can we do that? Yes, use set, right? We use set. So actually, each event can be represented as subset of the sample space. So we say, okay, the first event we just mentioned, right? Odd dice point can be represented by what kind of set? Yeah, 1, 3, 5, right? So it is a subspace. It's a subset of the whole sample space. And also, the second event we just mentioned, I want to say the event that the temperature is between this range, right? So it is also set, right? It is also, but it's infinite set. It is a segment. It's a range. But this range must be contained in real numbers, real value domain. Right? This is our sample space. So from mathematical theory, we use subsets of the sample space to represent different kinds of events. And then, can we use different events to compensate new events? So given given A1 and A2, right? And it can be combined as a composite, a new event by using both A1 and A2. For example, A1 could be the depth, the point in the depth less than 2, right? And A2 could be the point of depth is no, it's not good example. Let's just assume less than 4, right? And A2 could be the depth, the point of depth is even. And now I want to ask, what will be the event that both A1 and A2 happen? This is a new event. I can define it with my natural language, right? I define, okay, I want a new event to be that even A1, even A2 simultaneous happen, or both happen. Then how do we represent A3? Using mathematical operations.
You're even A1 and A2? Or the intersection of A1 and A2?
Yeah, exactly right. So to construct more complex events, we can use set operations. So this particular type of composition is called, they both happen, right? Then we use intersection. So we can write it as A1 intersect with A2. Right? So if A1 intersects with A2, what kind of set do we have? Yeah, 2, right? So now let us check whether this set, which only contains one element, 2, whether it corresponds to this event. Both A1 happen, both A1 and A2 happen. It indeed corresponds, right? A1 means that your dice, the point on the depth is less than 4, right? So it can be only either 1, 2, 3, right? And A2 is that it must be even. So if it both happen, then there's only one possible outcome is 2. So this is one way to construct the event. Another typical way to construct a new event is that A4. I define A4 as A1 happens or A2 happens. And now for this new event, how can we use the set operation to construct A4?
A1 union A2.
Yeah, union, right? So it's very natural. We use set theory. So now it is A1 union is A2. And then we can combine multiple events, right? And by using either the intersection or union to create more complex events. So that's about the events. And also, for those events, we want to assign a probability. So what is probability? Probability is just a number between 0 and 1. Right? So it must be between 0 and 1. And then we have a very intuitive properties for probability because the event, remember the event is represented by a set. Right? So if like event A1, the corresponding set is contained in A2, then what will be their relationship of their probabilities?
Probability of A2 greater than.
Yeah, that's very natural, right? Because you cover more possible outcomes. Right? So if A1 is contained in A2, then probability of A1 must be no bigger than probability of A2. And also, for the whole sample space, what is the probability of whole sample space?
1.
Yeah, 1, right? This is a very basic point. And what is the probability of empty event?
0.
0. 0, right? And this stuff's talking about random events or random things in terms of sample space. But remember, we defined the random variables. So random variable is mapping from sample space to some mathematical domains, typically like random, like real numbers or some integers. So now we can come back to the random variables. So talking about random variables, a very important concept is called cumulative density functions, CDF. So what is cumulative density function? There is a connection, strong connection from this event-based probability theory. It's usually called classical probability because it's talking about how to gamble it. This is the origin of modern probability theory. And then when we define the random variables, we rigorously define random variables, we move to the modern probability. But the basic properties related to each random variable is also associated with the definition of random events. Why? Because the CDF, cumulative density function for a random variable x, right? Here, x, big X is the random variable, and small x is some value. It's not random. It's simply defined as the probability of a special type of event. So what's a special type of event? It is a probability of the event that the random variable is smaller or equal to the given input x. So this is the definition of the CDF of a random variable. So now we can say the CDF is just the probability. Then what kind of property do we have immediately? Yeah, that's a great point. So first we should be aware that because CDF is a probability, essentially, so it must be a non-negative, right? Probability cannot be a negative. And then it must be no bigger than 1, right? Otherwise it's not probability. So the probability density function must be between 0 and 1. And the second thing is that when you increase the input of the CDF function, right? When you increase x, what will happen for this probability? Yeah, increase, right? When you increase x, then the event, the corresponding set, right, is also larger, right? Larger and larger. Then the probability will get larger and larger. So essentially, CDF function is a monotonically increasing function. Increasing function. So typical curve for CDF function is just like this. So here's the x, the input for CDF function, and it cannot exceed 1. Sorry, here is 1. And as long as x increases, your function value increases. But finally, when x approaches to infinity, the CDF will approaches 1. So this is a basic property for CDF. And then the question is, how can we calculate CDF? How can we calculate CDF? Yeah,
integral?
Yeah, integral, right? So actually we consider two cases. Right? If x, the random variable x, is discrete, then how can we calculate? So, yeah, we can solve it because when random variable x is discrete, suppose it can take like 1, 2, 3, blah blah until n, right? And we can use a table to represent its probabilities at each possible value. Typically, here's x and PRx, right? And we have 1, 2, 3, blah 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 until n, and we have p1, p2 until pn, right? And to calculate the CDF value for x at any input x, right? We just query the table to find out the values that is smaller than or equal to x, and as all the corresponding probabilities, then we get the CDF. And then what if X is continuous? Yeah. When things become continuous, the discrete summation becomes is generalized into integration, right? And then the function we are integrating out is called PDF. So PDF is usually denoted by a small f and indexed by the random variable x, and this is the input of x. So the CDF is actually an integral. The lower bound of the integral is minus infinity until the target function, target input x, and in the inside integral it is the PDF. And here, to avoid confusion, I use t, right, and over dt. So if you treated this integral as a function over x, right, or the upper bound, so we can immediately get this from calculus. When we take derivative over the CF, you get the CDF. We get the PDF. This is how we calculate this is the relationship between CDF and PDF. And also, this discrete case is a special case for the PDF, because in discrete, when x is discrete, the numbers in this table actually correspond to the PDF, right? And the integral is degenerated to summation. But of course, there is no derivative here because it's discrete. It's discontinuous. But essentially, they are in the same framework.
Is that integral from negative infinity to x?
Yeah, to x. So x is so let me denote here. X is the input of the CDF, and here the integral is with respect to this PDF function. Any other question about this?
So the bottom one, is that a partial derivative, or is that just a normal?
Oh,
is that just a normal derivative?
yeah, maybe I should. Partial derivative is kind of more broadly used, but you can use this D. Yeah. Any other questions?
I do have a question. Remind me, what does CDF stand for?
Cumulative density function.
Thank you.
So I guess these are pretty much which is covered in the last lecture, and today we're gonna continue the probability review. So we're still looking at this random variable x, right? So we know that the random variable x is not deterministic. Right? Usually it could have take many values. Right? Here, or here, more likely to be here, and less likely to be in far away. Right? So then there naturally comes a question that whether we can find out a constant, a fixed value, which can characterize the property for this random variable. So we'll review two very important properties regarding the random variable. The first one is called expectation. So what is expectation? Average? Yeah, expectation is average. So you can consider that because x jumps far away, back and forth, it's not deterministic. But what we want to know? We want to know that on average, what is its position? And when you take the average of its all possible values, you should consider how likely it appears in different locations, right? If it is more likely to appear the positions around here, obviously we should consider a higher weight in the average, right? If it is very likely to appear here, right, then we compute the average. We should give a much smaller weight over this position. So that's how we calculate the expectation. Expectation is essentially a weighted average, and the weights are the corresponding probabilities or PDF. This is called expectation. So let me write down the formal definition. So again, if X is discrete, like in this form, right? We use a table to represent the PDF. Each row corresponds to the specific value X can take and the corresponding probability. Then expectation is computed as the weighted summation over each possible value it can take, multiply with the corresponding probability. So here it would be 1 times P1. Right? And the second value it can take is 2 times P2 plus until the final value, the last value it can take is Pn is n times Pn. That's for the discrete case. And what if X is continuous? How can we calculate its expectation?
Is it the integral of X of the value times the PDF?
Yes,
value?
exactly. Right. So similar to the case for the calculation of CDF, right? When we have an infinite uncountable number of possible values X can take, we use integration. So when X is continuous, we need to depend on the continuous PDF function, which is an integral. And remember, this integral is over the entire domain, which contain all possible values X can take. Right? And inside this integral, we integrate with all possible value X and multiply, that is weighted, right? Weighted by the PDF function, probability density function, dx. So this is a continuous case. So now let us look at what kind of properties do we have for expectation. So actually expectation is very nice operation. If you treated the calculating an expectation, the expectation of a variable, a random variable as an operator, it's a very nice operator. Because first, if we get a new random variable by adding them together, X and Y, right? If we want to calculate the expectation of X plus Y, it is simply to be the expectation of X plus the expectation of Y. No matter whether X and Y are continuous or discrete, or one continuous, one discrete, it doesn't matter. And this is very easy to prove following the definition. And also, if we multiply a random variable X by a constant, say, like C, and then take its expectation, what can we get?
C times the expectation of it?
Yeah, we can simply move C outside of the expectation. So it simply is C multiply the expectation of X. And from these two basic rules, what can we get if we do the expectation of a linear combination of two random variables, like AX plus BY. And here A and B are both the constant, fixed constant, not random variables. It's simply to first calculate the expectation for each random variable, then do the same, exactly same linear combination. Just AEX plus BEY. And actually, this rule generalizes to arbitrary number of random variables. So suppose we have n random variables, x1, x2 to xn, and we have their linear combination to be like this, AI, xi. If we want to take the expectation of their linear combination, is simply all we need to do is simply to move expectation inside the summation over each random variable. That's it. That's the expectation, concept of expectation and their basic properties. And in future, we will enter the machine learning class or data mining class. You will use these properties again and again, repeatedly. And any questions regarding this? We are interested in the total height after the man wears the shoes. And this total height actually consists of two parts. One part comes from the height of the man himself without any wearing shoes. And we assume his own height follows a standard normal, or not standard, just a normal distribution. And later we will introduce what is normal distribution. But here, we just assume it follows some distribution, some specific PDF. And we know that expectation of this own height is 1.755 meters. And another component which determines the total height is the thickness of the shoes he wears, S. That is denoted as S. And here we assume S is discrete. It can take four values, like 1 centimeters, 2 centimeters, 3 centimeters, and 4 centimeters. And here we give this probability for taking each value, right? Taking each value. So the probability of the thickness being 1 centimeter is 0.1, 2 centimeters 0.1, 3 centimeters 0.5, and 4 centimeters is 0.3. And now we want to know the as denoted H, the expectation of the total height when the man wears his shoes. Now how can we calculate this expectation? Yeah. So first we need to know the relationship between H and the big H and S, right? So obviously it is a summation, right? The total height is his own height plus the thickness of his shoes. And now we want to calculate the expectation of total height. According to what we have mentioned, right? The expectation of total height is the expectation of his own height plus the thickness. Then it is equal to the expectation of his own height plus the expectation of the thickness. So for the first one, we know that the expectation is 1.755 meters, right? And for the second one, how can we calculate the expectation for the discrete random variable?
Each value times.
Yeah.
Basic probability.
Yes, each value times the probability. So here we can simply calculate the expectation of thickness is to be like 1 centimeters multiplied with this probability 0.1, and 2 centimeters multiplied corresponding probability 0.1, 3 centimeters multiplying 0.5, and 4 centimeters plus 0.3, which turns out to be 3 centimeters. And now we plug in here. So here we have a 1.755 meters, which is 175.5 centimeters plus 3 centimeters. The final expectation is 178.5 centimeters. So this is one example of it.
Do there have to be independent variables for this to apply? Or?
No, there's nothing to do with the independence. That's a nice property of the expectation. But if you calculate like other statistics like covariance, which we'll cover immediately, we'll talk about immediately, it doesn't have such kind of nice properties anymore. Any questions? Okay, great. So now I have discussed one very important properties regarding the random variable x, right? This is the expectation. So we have another very important property of x. To know, right? So intuitively speaking, we are also interested in the spread of x, right? Remember, x is a discrete, is not a deterministic value, right? It can change, right? So naturally, we want to say how far away it can jump, right? If it is jump very far away, okay, we know this x is this random variable is quite non-deterministic. If x is only its range is only in a very small range, we say okay, x is more predictable. Now, how can we evaluate the range x can jump back and forth? We use variance. That's called variance. So what's the definition of variance? Variance is simply another expectation. But it is not expectation on x itself. It is expectation of a square distance. So what kind of square distance? It is expectation of the distance between each value x can take and x's own expectation. This is called variance. So you can say, suppose this is the average of x, right? So every time when x takes a value, say here, some specific value x can take, and we calculate the square distance here, right? And then when x jumps to another location, then we calculate the square distance here. And we calculate the weighted average of all those square distance. We end up with the variance. That's the definition of variance.
Like how much it varies from the expectation, or how much it can vary.
How much variance it can?
Yeah.
This, you mean the x value?
Like if you, like the way I've always thought of it is like if you have your expected value, like variance refers to how much it can deviate from that.
It can be very, very far away.
Yeah.
Like for continuous random variable. So typically the sample space consists of all possible real values. So even the distance between x and ex could be like infinity. But it doesn't matter because it will be weighted. So it is very rare that x is extremely far away. So when we calculate the average, the weighted average, the weighted sign is huge distance is almost zero. So when we multiply together, just cancel. So finally, we still end up with a finite variance. But there could be the case that the variance of some random variable is not finite. It is possible. Any other questions?
So in order to calculate the variance, we need, if it's discrete, we need like a chart of x and its probability.
Yes.
Is that all we need? And then
Yeah, we need. Yeah, we must know the probability of x. Right? Otherwise, how can we calculate the weighted average? The weighted average, remember, x expectation is always with respect to the probability. The weights are calculated from the PDF. Yeah, but sometimes when we use some, for example, if you know some other statistics, then you can directly arrive at variance x. That's right now I want to discuss. So actually, this is the original definition. And we'll see that it is exactly the same as the expectation of x squared minus the square of expectation. So of course, if you have already if you have already known the expectation of x and expectation of x squared, then you can calculate the variance directly. You won't need to look at the PDF again because you have enough information to calculate. And this is very important and very useful property regarding the variance. And how can we derive from the original definition of variance to here? It's actually quite simple. So we can do it more. So first, this is a square term, right? The square of a subtraction. So we can expand it. We can expand it first. So so for this two terms, summation, subtraction, take expectation, I will end up with three terms, right? The first term is square of x. Right? The second term is square of ex, another term. Right? And the third term is a cross term, because the cross term appears twice. So we have to multiply a 2, the factor of 2, and x times the expectation of x. That's the direct expansion of this square term. And now we know that this is an expectation over the summation of several random variables, right? And we can immediately apply the rule we talked about the expectation, right? That means we can put the expectation operation on each item inside. Right? So we have a expectation of x squared. This is for the first term, right? And second term is expectation over the square of expectation. And third term is expectation over minus 2x and the times expectation of x. And we can look at these three terms one by one. The first term is just the expectation of x squared. And what about the second term? So remember, expectation of x is a constant, not a random variable anymore. So now that it is a constant, if you take expectation, it is constant itself. So here is simply the expectation, the square of expectation itself. And how about the third term? So for the third term, expectation is constant again, right? And minus 2 constant. So minus 2 multiplied with the expectation is a constant. We can simply move it out. Right? So let us move it out. This is minus 2 expectation of x. And then inside this expectation operation, there's only x left, right? So now this is third term. And now we can take a look at the summation of the three terms, right? So the second term is square, 1 square of ex, expectation of x. The second term is 2 square, 2 times the square of ex, right? And then when they are as together, we get minus square of expectation, right? And then plus the first term, we end up with this. So first, what does this tell us? We can first take a look at the variance of x. Right? Variance of x is an expectation of a square distance, right? So each term, each possible value in calculating expectation is always non-negative. Then what about their expectation? If you calculate the expectation of, let me write as y, right? If this random variable is always non-negative, then what about the expectation? Yeah, it must be non-negative as well, right? Similarly, here, the square distance is always positive, no, non-negative. Right? Square distance is always non-negative. Then the expectation of square distance is non-negative as well, right? So with that being said, the variance is always no less than 0. And now we can say, because variance of x is equal to expectation of x squared minus square of expectation. And we know the variance is always non-negative. So we can immediately obtain that this formula is non-negative. And then we can get, from this inequality, we can get is expectation of x squared is no smaller than the square of expectation. Yeah, this is about the variance. So what kind of properties do we have for variance? I mean, in addition to this observation, do we have similar property for the expectation operation? Unfortunately, no. We don't have such a similar property. If it is, then many like machine learning and data science computation will be a lot more easier. So why? We can take a look.
Isn't variance just another expectation too? Why can't we do the same thing?
Yeah, the problem is that the variance and the expectation of x itself, here I mean, doesn't have the same unit. Expectation is expectation over x itself, right? But the variance is expectation over some square value. When you take the square, things becomes much more complex. So we can start with some simpler case, right? Suppose we have a random variable x, right? And we multiply x with a constant scalar c. It's very similar here. So now we want to look at what will be the variance of c multiplied with x. So will it be c times variance of x directly? The answer is no. Because, as I just mentioned, they have different units, right? So actually, we must, if we want to move c outside of the variance operation, we must take a square of c. Why? Because we can prove that through the definition, right? So variance of cx is expectation of cx, right? Minus the expectation of cx itself, and then take square. So now you can see c multiplied here, and the expectation of cx is c multiplied with ex, right? So we can put c outside, but remember c here we have a take square. So when we move c outside, it becomes c squared. And multiply with x minus ex and square, and then we'll take the expectation here, and then we come here. And then this is one property. Another property you should be aware is that when we calculate the variance of x and y, the summation of x, y, usually we cannot obtain this. That means we do not have this simple summation that variance of x plus variance of y. That won't work unless x and y are independent. In this case, in calculating the variance, you must consider the independence, the problem of independence. So this is regarding the variance, and be careful, especially if you want to use this kind of stuff. And then the variance is talking about the spread of change of random variables. And then what about the co-change of two random variables? So suppose we have two random variables, x and y. So now we want to say how x changes relates to y's changes. So if x changes quickly and y changes quickly as well, we say, okay, their co-change or their correlation is quite strong. if it's x increases, y decreases, it's kind of negative correlation. If x increases, y increases as well, it's positive. This is called positive correlation. And how can we measure their co-changes, which indicate their correlations? So that's how we generalize variance for a single variable to two variables. It's called covariance. So the covariance is defined as an expectation of a multiplication. And the first term in the multiplication is x minus the expectation of x. And the second term is y minus the expectation of y. This is the definition of covariance. So obviously, when x is exactly the same as y, so that these two terms are the same. And we come back to the square, right? So we'll come back to the variable. But if x and y is different, then it calls covariance. And we can show that the covariance of x, y, this is our original definition. It is the same as the expectation of x multiplying with y minus the multiplication between x and y's expectations respectively. And proof is very similar to how we derive the definition of covariance. So we can simply expand this term. And when you do the expectation calculation, you'll cancel the terms, and finally you end up with this. So I'll leave this as a practice for you. And going back to the question we just mentioned, right? What I'm saying that we have mentioned that the variance of x plus y is not equals, usually is not equal to variance of x plus variance y directly. Right? And then what does it really equal to? We should correct this summation by some covariance term. So basically, it is equal to the variance of x plus variance of y, and then minus variance of x and y. So now, as we just mentioned, the variance takes a different unit from the expectation, right? So now if we want to obtain the same unit, what should we do? We can simply take a square root over the variance. So we name the square root of the variance as the standard deviation. So it's simply the variance, the square root of the variance of x. And what's the usage of standard deviation? We can combine it with the expectation to determine the specific range x more likely to appear. For example, if x is simply scalar, then we can use x minus standard deviation of x and x plus standard deviation of x. Right? We know that this is a place that x often appear. Right? So basically, suppose this is standard deviation, this is the expectation of x, then this range, expectation minus standard deviation of x, and expectation plus the standard deviation of x. And we know that, okay, this kind of range, x is most likely to appear. And then let us take a look at an example about how to calculate the variance. So we're going back to the shoe case. Right? So now let us simply look at the variance for the thickness. How can we calculate the variance of the thickness according to this discrete PDF?
expected value is x squared.
Yeah. And then weighted average, right? So we can try to calculate. So the variance of S is what? So first, we have already known that the expectation of S is 3 centimeters, right? And then to calculate the variance, according to the definition here, we just need to calculate the weighted average of each square distance between S and its expectation. And we can take a look because X only takes 4 possible values. So first one X takes 1 centimeters, so the square distance will be 1 minus its expectation, which is 3, right? And take the square and weighted by the probability, 0.1. And when S takes 2 centimeters, the square distance will be 2 minus 3 squared, and weighted by the probability 0.1. When S is 3, and 3 minus 3, the square distance is actually 0. And multiplying with the probability 0.5, and finally, the 4 centimeters minus 3 is squared, multiplying with 0.3. Then you get the variance. And how about the calculation of the variance with respect to continuous random variable? Integration, right? Again, it's integration. So for continuous random variable x, we have this continuous PDF x, right? And again, to calculate the variance of x, we integrate in the entire domain for x, right? And in the integration, we need to calculate the square distance between each x and the expectation of x, right? And take square, and weighted by the probability density function, right? And to the integration, because in a continuous space, summation becomes integration. That's it. So the expectation and the variance are probably the two most important statistics with respect to the random variables. And even for many famous distributions like normal distribution, also called Gaussian distribution, the whole distribution itself, namely the PDF, are purely determined by the expectation variance. This is a Gaussian distribution. And this is about expectation and variance. And then let us look back to the random variables itself. So far we have discussed what we have focused is just one random variable, right? But in our practice, we often need to look at more than one random variable. So in data science, we usually need to look at like hundreds of thousands of random variables at a time, and we're looking at their relationship, their mapping, such kind of things. So we must know the basic framework to model multiple random variables. Let us start with two random variables, say x and y. So for x and y, similar to the single case, we can also define CDF. This is called joint cumulative density function for the two random variables x and y. So let us denote as fxy and xy. What's the CDF for x and y? It is simply another probability. It's very similar to the one variable case. It's the probability of another special type of event. The event is that the x must less than or equal to small x. At the same time, y must less than small to small than the small value y. So this is the definition for the joint CDF for two random variables. So if there are multiple random variables, say x1 to xn, then we can also define joint CDF function for this n random variables, which is actually a direct extension of this probability, right? To be like probability of x1 less than small x1, x2 less than small x2 until xn less than small xn. So this is a joint CDF. And how can we calculate the joint CDF?
By multiplying the probabilities.
Do we double it?
Multiply. So it's a bit of different. And if you want to multiply them, it must satisfy some properties. So basically, we can also start with the discrete case, right? Suppose x and y are both discrete random variables. And then we can use a table. We can also use a table to represent x and y, and their probabilities. So suppose x can take 1, 2, 3 to and 1, the y can take values from 1, 2, 3 to n2, right? And then we can use a table to represent the probabilities for each specific pair of x and y. So here it could be p11, p12, and p1n2, and this is p21, p22, until p2n2. This is pn11 until pn1 and 2, right? And then to calculate this CDF, what should we do? For each specific x and y. We can simply look at the table, right? We can simply look at it for each specific x and y. We just find out the rows and columns which the corresponding x and y is smaller than x and y, right? And then we just add the corresponding probabilities together. Similar things for one dimensional case, one variable case. So suppose x is 3.5 and y is 2.5. We just look at, okay, all columns, all rows, which indicates x, right? It at most to be 3, right? The first 3 rows, right? Because 1 to 3 is less than or equal to 3.5, right? And then we look at the row, we look at columns, and most 2.5, right? So we add most the first 2 columns. Because y can only be 1 or 2, right? Y cannot be 2.3, because 3 will be bigger than 2.5. And then we just find out the region that x and y takes values are both less than this pair. And then we calculate the corresponding, we add the corresponding probabilities together, we get the CDF. Any question? Okay. So this is for discrete case. So how about the continuous case? Again, we need to utilize the integration. So in the continuous case, we need to introduce the joint probability density function. It's called joint PDF. So it is denoted by, again, small f x and y and x and y. And then for any particular value of the joint CDF, it's simply the integration. But here we have a double integration because we have both x and y. It's double integration. So for x, it starts from minus infinity and to the target value x. And then for y, it starts from minus infinity to the target function value y. And inside integration, there's our joint PDF. And here, to avoid confusion, I use u and v. So here we integrate u and v together. So here x and y is denotes the target, the input, the specific input for the CDF. And also from this form, we can see that because this is actually integral function, right, with respect to the upper bound. So we can know that the joint CDF is essentially the partial derivative of the joint CDF because it's two partial x and partial y. So this is directly from calculus result. And then given the joint PDF, again one thing that in the discrete case, this table of probabilities is actually defined the PDF, right? But it's discrete. Of course, there will be no such kind of derivative forms, but then the integration is deteriorated to the summation. So everything is similar to the one variable case. So this is the definition of joint CDF and joint PDF. And then given the joint CDF and given the joint PDF, f, x, y, here's indicate the random variables, and x, y is the input term. And then we can define a conditional density function. So conditional density function is denoted as x given y. We actually were interested in when the random variable y takes some value, what is the probability distribution of x will be. That's why we define the conditional density. So conditional density is defined as the joint density over the density of y itself. Then here comes the problem. How can we obtain the density of the random variable y itself? We can use marginalization. Means that we can directly calculate the density of y itself by marginalizing over the joint density. So marginalizing is essentially a integration as well. So this is called marginal density. Marginal density of y is just integration over the joint density. But here, it just integrates over x. And remember, it is integrated over the entire domain of x, such that we can remove x. And similarly, if we want to calculate the marginal density of x, then you just integrate out y in the joint density. So this is the definition of the marginal density and the conditional density. And what's the usage of conditional density? We can use it to determine whether the two random variables x and y are independent. So if two random variables x and y are independent, we're actually saying that the conditional density of x given y is exactly the same as the marginal density of x itself. So this is the definition of independent. But from the definition, you can immediately obtain an equivalent definition. That means when x and y are independent, then the joint density is equal to the marginal density of x multiplying with the marginal density of y. So this is, yeah, independent. Only when they are independent, you can say that. But here there's a small restriction. You should be aware that when we define a condition density, we must ensure that this marginal density is not zero. So it's kind of a corner case that should be aware, because when you divide something by zero, it's meaningless.
Is this an if and only if relationship, the x and y being independent and the conditional equaling the marginal?
Yes.
Okay.
Let me write down. These three conditions are the same. The three conditions mark the conditional density of y over x is exactly the same as marginal density of y. Is equivalent to say the conditional density of x over y, x given y, is exactly the same as the marginal density of x. And is equivalent to say the drawn density of x and y is equal to the product of marginal density of x and marginal density of y. They are the same thing. And then when any of these three conditions satisfied, we can claim that x, y are independent. So basically, from intuitively speaking, you can see that because, okay, given whatever y takes value, the distribution of x is itself. Doesn't matter. So you can say intuitively speaking, it actually indicates the independence. Independence means x has nothing to do with y. So whenever you take your condition on any value of y, it doesn't affect the distribution of x. So now let us give a simple example to compute the marginal density and marginal probabilities. So suppose we have this is still discrete. Right? So we have two random variables, S and P. S represents the color of shirts, and P represents the color of pants. And some guy just randomly pick up a t-shirt, a shirt, and randomly pick up a pant to go to the job every day. And suppose he has three kind of shirts and two colors for pants. So we can represent the probability, the probability in a two-dimensional table, right? So here is S, and we have a green. We have a possible green shirt, and red shirt, and blue shirt. And for pants, we have two colors. We have a blue pant and a white pant. So now we know their joint probability, or in other words, the joint PDF here in this table. And let me write it down. It's 0.3, 0.1, 0.2, and 0.05, 0.2, and 0.15. So now, given this joint PDF, how can we calculate the marginal probability for S and the marginal probability for pants? So for example, what is the marginal probability of S equals to green?
0.3 plus 0.05.
Again, according to the definition of the marginal probability, we should integrate out the other random variable, which is the P, right? The color of pants. And for the discrete case, we simply add them together. So for the specific probability for S equals to green, when we add out all the possible values of P, we're actually adding according to the column, right? So in other words, PS equals to green equals to what? PS equals to green and P pants, right, is blue, plus PS equals to green and pants is white, right? Because we only have two possible colors for pants. And when we calculate the marginal probability, we should integrate out all possible pants colors. So we have two possible pants colors. So add them together. Any question at this point? That means we just add the two items here. So we end up with the marginal probability for shirt color to be green, which is 0.35, right? And similarly, we want to calculate the marginal probability for shirt to be red. What can we get? Yeah, we just add this together. We add the probabilities that P equals to blue and P equals to white when S takes red. So it's 0.3. And for blue, we have 0.35, because we add this and this. And then how about we calculate the marginal probability for pans? So how about the probability that pans is the pan is blue and marginal probability of pan is white? How to calculate?
Adding probability of green, red, and blue.
Yeah, we add them according the row, right? Because we need to integrate out the shirt S. So for each specific value for P, we ask all the probabilities where S take different values. That means we need to sum according to each row. 0.3 plus 0.1 plus 0.2. Here we get 0.6. And similarly, the marginal probability for pan to be white, what do we get? Add them together. So 0.25, 0.2, 0.1, 0.4. So this is the case to calculate the marginal probability for discrete random variables. And obviously, if these random variables are continuous, the summation is replaced with integration. Okay, I think this is pretty much we will end up here about the probability knowledge. And on Wednesday, I will give you a simple snippet of code showing the PDF and CDF of normal distribution. And because in your homework, you are required to draw the PDF, CDF curves for another type of the random variable. But you can also look at the course material, which is shared in my course web page. You can directly look at the piece of the code. It's very, very simple, just 2 lines. Okay, see you on Wednesday.